So linear programming problem, this is basically used to maximize or minimize some numerical value representing profit, cost, production, quantity, etc. To understand the linear programming problem, you need to know little bit of its history also. It was invented and developed by great mathematician from USSR. His name is Kantarovich. He developed the subject, but people in World War II started using it to estimate opponents' actual power, because they wanted to fight by knowing their uh, by knowing the opponent's resources, what way they can fight, and they can arrange themselves accordingly. Not only that, nowadays linear programming problem is being used by uh, people in this field, as well as they are being appointed by uh, some companies to maximize the profit and to minimize the cost. This is a very important kind of optimization. You may ask, why linear programming problem? Why we are not talking about maximum minimum we have learned in calculus? My answer is, in calculus, function may not be linear, it is non-linear. Maximization of a function, rational function, where quadratic numerator and linear function denominator or cubic in denominator also possible. But here linear programming problem, the main advantage is all functions you are going to maximize or minimize, they're linear. Okay. And the second thing is, it will solve the purpose of using mathematics in a problem being faced by management of a company. Direct application. Okay. And this linear programming problem is a branch of operations research. Some of you may study in higher classes. Those will pursue chartered accountancy, those will pursue mathematics, MSc, or some engineering subjects, production engineering. This operation research plays an important role, and linear programming problem, better to say language of this. If you don't understand linear programming problem, you cannot solve, you cannot start operation research. It's like that. Okay. The most useful part of mathematics in daily life, probably this one. After mathematics in computing in other, I think this has wide application in other subjects also. Commerce, economics, any branch where you want to maximize a linear function, linear programming problem plays a very important role. Okay. Here in linear programming problem, we use a very important technique which is used to find the optimum resource utilization, and it consists of two terms such as linear and programming. Linear defines a relationship between many variables with degree 1, and programming defines the process of selecting the best solution from various alternatives. Okay. Not only in mathematics, you see economics, business, telecommunication, manufacturing field, it has wide application. And simplex method is the next version of linear programming, which we'll study in higher classes. Okay. What are the components of linear programming problem that you have to understand? Basic components of linear programming problem are like this: decision variable, constants, data, and objective functions. Decision variables whose maximization or minimized value will help you to maximize the profit or minimize the cost. I'll give you example. the general linear programming problem will be like this: maximize or minimize this objective function. This is called objective function. Maximize z equal to this thing, subject to these conditions like c1 x1, subject to these conditions a1 x a11 x1. This is in matrix form, we can write. Basically what you are going to do, that I'll explain. First I tell you the mathematical part. It is better I revise the mathematical part, where you will find the application of class 11 linear inequation concept in linear programming. Basically those who have developed concept over there, those who have got the right concept over there, they can excel here also. Okay, linear programming is entirely based on linear inequation concept. Okay, if I take a maximization problem, first think mathematically, then I'll give you two examples of it. Like I'm taking one textbook problem from your textbook only, exercise 12.1, which we are going to maximize or minimize with the given conditions. Okay, like suppose I am taking this one, number 4. Maximize z is equal to say 3x plus 5y, subject to the condition that x plus 3y, subject to x plus 3y greater than equal to 3. Wait a minute, then this will be a minimization problem. For maximization problem, it will be just changing the sum. Let me do a maximization problem first. 3x plus 2y. This is sum number 5. Then we will solve a minimization problem. Subject to this condition that x plus 2y less than equal to 10, x plus 2y less than equal to 10, 3x plus y less than equal to 15, and xy is greater than equal to 0. We want to maximize this function subject to this condition. Learn mathematically first. And the most important condition in linear programming problem is that we must find a graphical solution over there. And the thing is that you will be ready next class by taking a graph with you. Here I am drawing the sketch of every inequation roughly, but there is no problem in calculation because that calculation will do by actually solving the equations. Okay, so here an xy greater than equal to 0. The most important thing about linear programming problem is this feasible condition, feasibility condition. Always solution will lie in the first quadrant, because later on you will find that this xy actually representing number of units. When you are producing something, when you are manufacturing something, these x and y, they are variables, decision variables. Those decision variables can never be negative. So non-negativity condition must be there. Okay, now let me plot this. First one is x by 5. Say this is 1, 2, 3, 4, 5. This is 10 and this is 15. Here also the same manner. This is 5, this is 10 and 15 in the graph. Now let us plot the first line. Why I am doing so? Because here I will use this one as A linear, yes.
Where did x and y come from the first one?
First one, it is coming x by 10. Yes, it is x by 10. X by 10 plus y by 5, right? So this one is 10, 10 comma 0, and next one is 0 comma 5. So graph of this to be considered. The way we do it for linear inequation graph. Now is 0, 0 satisfying it? Yes, it is satisfying. So region will be towards the origin. Before we apply non-negativity condition, this will represent a straight line and it is going towards the origin. You can extend it. There is no problem in extension because you cannot consider all the conditions in one step only. This is just plotting of this inequation. Now let us plot the next one, x by 5, using different ink for this. You may not use different ink, you use pencil only, one color, no problem. And next one is up to 15 here. So this one is C. This one going to be D, 0 comma 15, and this is 5 0. And here also you see, if you put x equal to 0, y equal to 0, the region is directed towards the origin. And then we apply the non-negativity condition. What is that? You can see in the diagram non-negativity condition that xy greater than or equal to 0, the solution must lie in the first quadrant. So xy greater than or equal to 0, it means the region will be in this manner. First quadrant only. Like this. So what is their common region there? The common region you all can see, it is the region bounded by the two lines given here, the pink one and the green one, with the x and y axis. So this is going to be our common region. We will shade this one. I have the scope to shade it with different color. So this region, this color, what will you say, pink, biscuit or yellow, whatever you say, this is going to be the common region and this is the point P on it. Every time, no, this is not a common region because this part will not be satisfied. Take care of this. This part will not be there because the green region, the green one, the green line is not covering that part. So this is our common region. This is common region. Everyone able to write the coordinates of the quadrilateral here. So feasible region, you will write this manner. Feasible region is OBPC, where O is 0 0, B is 0 5. P we can get by actual solution if you solve it. It's just actual solution. This in exam you will get it from the graph only, but here we have to do by actual solution. This you write x plus 2y. Don't show this calculation, never. Even if you are verifying it, never show it there. So multiply second equation by 2. This is going to be 6x plus 2y equal to 30. This we are doing separately, not showing in actual calculation. So this is minus 5x. So x is 4. Y is 10 minus 4, 6. Y is 3. So P point in graph you will find this as 4,3. This you have to get by counting. So and the point C is going to be 5,0. Remember the maximum or minimum value will lie at these corner points only. Now we take care of the objective function, that Z. Z at origin is 3 into 0 plus 2 into 0. Z at B is 3 into 0 plus 2 into 5, that is 10. Z at P is 3 into 4 plus 2 into 3, that is 18. Z at C is 15 plus 0, that is 15. So you all can see the maximum value occurs at P. The maximum value, so maximum value is obtained when we take x4 y equal to 3 and z max is equal to 18. This is a maximization problem. It is solved fully from your textbook. Only I have taken this. Let's see another problem where minimization is involved. Minimization, just I'll show you one sum because unbounded region concept they are going to delete. But at the same time, we must know what is there. This unbounded region is the minimization problem. Normally, in most of the cases, those unbounded case means minimization. So let us maximize that bounded region also may be there, but conditions should be stated. We'll do one unbounded one. This is going to be sum number 6 in your textbook. You all can see one minimization problem. Minimize z equal to x plus 2y subject to 2x plus y greater than or equal to 3, x plus 2y greater than or equal to 6. You can plot before I do it. So let me plot this. First, you treat the given inequation as equation only. 2x plus y equal to 3. So this implies x by 3 by 2. And this one, x by 6 plus y by 3 equal to 1. And this is greater than or equal to. So first one, if you are plotting that x by 3 by 2. Suppose this is 1. No, you take this is 1, 2, 3, 4, 5, 6. So 1.5 lies somewhere like this. Then 1, 2, 3. A, B. This point has coordinate 3 by 2, 0. And this one has coordinate 0, 3. This is going away from origin.
So in the question it is given z equals to x plus 2y, we have to find minimum value, and in the question it is already given x plus 2y is greater than or equal to 6.
Yes. So what is your conclusion? What will be the minimum value? Can you see that? From there only you can see that z equal to x plus 2y, you have to minimize by obeying this condition also. You must take 2x plus y greater than or equal to 3 into consideration also. Okay.
Okay.
So this one we plot that x by 6, y by 3, 1. This point is 1, 2, 3, 4, 5, 6. This one says 6, 0 and 0, 3. Here also it is going. See, this part is removed. The lower part is removed from there. This part will not be there. Now to find the minimization problem, to find the minimized value, we will first shade the region. We are shading the region this manner. Say you will do it with pencil only. If you are supposed to use different color, then it is understood. Otherwise, you have to shade the region. And in this region, you will find the corner points, as maximum minimum always lies at the corner point. C is the corner point. So minimized value, for minimized value, you have to find the value at ZB, that is 6, ZC, this is also 6. So you're getting minimized value at these 2 points. It implies that there is minimized value at any point on BC. Minimize your conclusion as you got minimized value at B as well as at C. So minimized value is obtained at any point on BC. That's why I took this example. Very interesting to note. Your answer going to be like this, not at a point, on a line. Infinitely many points it occurs, and the minimized value is given by Z is equal to, Z min is equal to 6. Actually, if it is a MCQ question, the way he was talking, you can take the minimized value as 6. But in board paper, you have to show everything by calculating. Okay. So these are two problems where region is bounded, region is unbounded. In case of bounded region, normally we find maximum. Here also minimum value can be found. If a question arises, you will say that minimum value occurs at origin at 0, 0. Similarly, region may be some other places. There also corner point you can find minimized value. But normally minimized problem, they give minimize this and greater than equal to thing. So that the region becomes unbounded. Now let us see one practical problem where this x and y have some meaning. It is not mathematical only. I told you this is the most useful topic after mathematics in computing. This is the most useful topic in modern mathematics. Mathematics always useful. Without maths, no one can take a single step. I am taking one example for cake preparation. You like Christmas is coming, and those who like cake, myself is fond of cake, but there is some restriction. I cannot take cakes frequently, but still I like it. Exercise 12.2, the problem I am going to consider, which is a cake manufacturing problem. One kind of cake requires 200 grams of flour, number 2 from exercise 12.2, and 25 grams of fat. Another kind, obviously this is not raw fat. Another kind of cake requires 100 grams of flour and 50 grams of fat. Find the maximum number of cakes which can be made from 5 kg of flour and 1 kg of fat. Okay, somebody is preparing. How many maximum number of cakes can be prepared? Here x and y has specific meaning, and I am taking the help of a table. Okay. Suppose the first kind of cake manufactured be x, second kind be y. And I am writing the amount. You can write other way around also, no problem. This is flour and this is fat. And total availability, this part stands for availability. How much fat, flour available over there? Flour available is 5 kilogram. In terms of gram, it will be 5,000. And fat available is 1 kg. That is 1,000 gram. Now, this required 200 gram of flour and 25 gram of fat. And this one required 100 gram of flour. Sorry, wait a minute. Flour required is 100, 200 and 100. Sorry, this part will be 100. Y require 100 gram for each cake. And here fat required first type of cake is 25 gram, and this one required this one require 50 gram of fat. Okay, two types of cake being manufactured. Let you'll start this manner. Let X number of first type and Y number of second type cakes are being manufactured. Okay, so the condition is going to be, see, this is maximum availability, no? So in flour, first if you have made X number, then flour required is 200X. All of you agree with me? Second one, if each cake requires 100 gram, for Y number of cakes, it requires 100Y. So 200X plus 100Y less than equal to 5000, because more than this is not available here. And 25X plus 50Y less than equal to 1000. And number of cakes cannot be negative condition. It's a common sense. Okay. So to solve this linear programming problem, we are going to maximize something. What is that? What do you think? That maximize J equal to cake, number of cakes produced. Maximize J equal to X plus Y, subject to these two restrictions. Okay. So to solve this one, again, we will treat the given inequation as equations only. First one, if you are solving, then X by 25, Y by 51, this one X by 40, Y by 20 equal to 1, and XY greater than equal to 0 already there. If you are going to plot, say this is 1, 2, 3, 4, 5, 50, and here also 1, 2, 3, 4, 5. Okay, X in this direction, Y in this direction. Let us plot the first line. The first line is 25, 1, 2, 3, 4, 5, 25 and 50. So let us join these two. If you extend more, there is no problem. This part is A, B, and we have taken this point as, this will write, never forget, we'll deduct marks. We'll be ready to deduct your marks if you don't write it this manner, the way we like. And 1, 2, 3, 4, this is C, 40, 0, and this is D, 0, 20. So this CD is going to be okay. Now both the regions, because less than equal to 0, the region going to be directed towards the origin. So if I don't have time, I'll simply write the common region as xy greater than equal to 0. So this is going to be the common region described by two inequations. This point all of you know. Point P in graph you will count and you will get. Let me do it here now. Just multiply first second one by 2 and subtract. $3,000. So 150x. X will be 20. Then y will be equal to 10. This will get by counting. From the graph only you will find it. Never try to solve it. If you want to verify it, you verify it and then cancel it. Or do at place where the examiner will not consider that it is a part of your calculation. So we have found graphically the point 20, 10. Then maximum minimum value we will consider at A. At A, ZA is 25. ZP is 30 ZD is 20. Obviously, Z is maximum when X equal to 20, Y equal to 10, and Z max going to be equal to 30. Okay.